Welcome to the second session of the day. So in this session there are going to be 3 talks, all on proof theory. The first talk will be by Bjorn Lellman, constructing cut-free sequence systems with context restrictions based on classical or intuitionistic logic.
So thank you very much. As mentioned, my talk is on constructing cut-free sequence systems with context restrictions for modal logics based on classical or intuitionistic logics. So I inserted the term modal logics just to make it, well, maybe a little bit clearer. Okay, so first, all of you know, I guess, that there are many, many modal logics around. So we have, for example, modal logics based on classical propositional logic. So for example, K or KT, K4, S4, or some conditional logics or what have you, everything. And we also have some modal logics based on intuitionistic logic. So for example, analogs of the classical or standard modal logics. So we have constructive K or constructive S4 or some access control logics or program logics or something like this. So the thing is, if you work with these logics, then usually you're also interested in deciding which formulae are theorems of these logics, right? So you want a decision procedure. And one way of doing this is via some nice sequence system. So you could have like a sequence system and do, or like a derivation system which is sound and complete for the logic, and then you can do backwards proof search, for example. You could try and come up with all the possible proofs for a formula. If you find one, then it's a theorem. If you don't, then it's not. Or you could try and use the subformula property of the sequence system and get decidability via some fixed point argument. So just like iteratively compute all the decidable formulae or sequence. So sequence systems are good for deciding logics, but of course the problem is that it's not always easy to find such a good sequence system. And well, our question is there some generic way or generic method, generic strategy to construct good sequence systems? So yeah, the idea is that you don't have to, the idea is to give you some tools to work with so that you don't have to invent everything from scratch every time you stumble upon a new modal logic. Okay, this question breaks down into three parts, basically. So the first is, what exactly do we mean when we talk about a sequence system? So which formats should the rules have? The second one is, well, okay, suppose we know what a sequence system is, suppose we know what a rule is, then what is a good sequence system? And finally, once we know what a good sequence system is, we would like to know how to construct one. Okay, I'll go through these 3 parts like one by one. So let's start with the first. What exactly is a sequence system for a modal logic? Okay, let me take you through some of the basics. I mentioned that we can construct sequence systems for modal logics over classical or intuitionistic propositional logic. In this talk, I'm going to concentrate on intuitionistic logics because the classical case is easier. And basically everything works as well, but it's easier. So as usual, we have, for formulae, we have propositional variables. We have the fault sum. We have propositional connectives. Plus, we also have a number of modalities. So this could be the box modality or the diamond modality, or in general, any n-ary connective or modality, which I would denote with hearts, for example. But you can basically insert anything you like. So since we're in an intuitionistic setting, we use asymmetric sequence, which read gamma entails delta. And so gamma is a multiset of formulae, so you can have formula with multiplicities, and delta is just a single formula. And as usual, the intended interpretation is that the conjunction of all the formulae in gamma implies the formula delta.
I assume heart is monoclonic. If it's not monoclonic, it will still work.
Yes, I'll come to that. Okay. In all our sequence systems, we are going to have axioms. Zero premise rules where a formula A occurs both on the left and on the right-hand side of the turnstile. So intuitively, this is A implies A, so it should be derivable. We're also going to have structural rules of weakening, so where we can add a formula on the left-hand side, or actually on the right-hand side as well, but Okay, so if something is entailed by gamma, then it's also entailed by gamma and A. We also have contraction, meaning that we can, basically delete duplicate instances of formula. And we also have the cut rule, which is basically the sequence-style analog of modus ponens. So if gamma entails A and A together with sigma entails pi, then gamma together with sigma entails pi. Okay, since we're working over propositional logic, we are going to have all the propositional rules. I'm not going to show them to you, but these are basically the standard rules. And we are going to have congruence rules for all the operators, hearts. And this is the only thing we need. So this is basically This basically means that you can substitute logically equivalent formulae under the modal operator. So in terms of cellars, these would all be classical modal logics, not necessarily monotone. Okay, so this is what we always have, and then we are going to have some additional rules of a specific format. Now, what are these going to look like? So we call them rules with context restrictions, and this is basically an abstraction of the format which all the standard logics, or most of the standard modal logics, come in. The main notion here is the notion of a context restriction, which is simply a tuple of sets of formulae. So we have a left component FL and a right component FR, and the intuition is that this tuple restricts a sequent by allowing only substitution instances of formula in FL in the left part of the sequent and only substitution instances of formula in FR in the right part of the sequent. Right, so we could say we only want to consider, or we could have a context restriction which restricts us to sequence which have only boxed formulae on the left-hand side and only conjunctions or disjunctions on the right-hand side. If we have this notion, then a rule with context restrictions consists of, well, some kind of principal formulae, which I will denote with sigma entails pi here. So this is a sequence of modalized variables. So you cannot have any propositional logic in there, or so just modalized variables. We also have a number of premises. A premise is a sequent gamma I entails delta I, which is just a sequence of propositional variables, together with a context restriction. So the modal rank drops by 1 if we go from the principal formulae to the premises. And the idea is that in an application of such a rule, we have a conclusion which consists of the principal formulae and some kind of context. And if we go from this conclusion to one of the premises, where the premise comes with the restriction Ci, then this premise copies exactly those formulae of the context which are which are kind of compatible with the context restriction or satisfy the restriction. So let's have a look at some examples. I think this will be the best thing. So as I mentioned, the rule format kind of encompasses most of the standard logics. So for example, if you take the K rule for the box modality with premise A, B entails C, and conclusion, some context gamma, together with box A and box B entails box C, then this is rendered in our new format, or in this new notation basically, as a rule with principal formulae box A, box B, box C, entails box C, and premise A, B entails C, together with the restriction with the empty set both in the left and the right component. Right, so this restricts, or this has the effect that we don't copy any formula into the premise because no formula is a substitution instance of a formula in the empty set. So for the second rule, the T rule, you notice that the whole context is copied into the premises, and we capture this by here using this restriction, which has just singleton P both in the left and right component. Every formula is a substitution instance of the propositional variable P, so every formula gets copied. So every context formula gets copied into the premises. On the other hand, we could also have some more interesting restrictions. So for example, the for rule, well, this box gamma means that we only copy the boxed formula from the context. And well, this can be captured as a context restriction which has the singleton box P in the left component and the empty set in the right component. So it copies only the boxed formula from the left-hand side of the conclusion. So this notion of a rule with restrictions is quite flexible. And well, basically everything which you can write in this way we can deal with, or can be possibly dealt with in this framework. All right, so now we know what a sequence system is. So let's have a look at what a good sequence system is. And since we're coming from this, well, one of the main ideas was to get decidability for the logic, so we want some kind of backwards proof search or some kind of subformula property for the sequence system. Okay, I should show this one. Sorry. Yeah, so that means that if you have a look at the structural rules which I showed like in the beginning, then there were the contraction rule and the cut rule. And if you view them from a viewpoint of backwards proof search, then these are really bad because, for the contraction rule, okay, more general in backwards proof search, we start with a sequent and we existentially guess a rule which might have been used to apply to derive the sequent, and then we recursively check all the premises of this rule that they are derivable, right? But if the last applied rule was a contraction rule, then in effect we are making the sequent bigger because we're just doubling up one of the formula. And well, you can do this like as often as you like, and you end up with basically an infinite branch in the search tree for the proof. And this is bad because then you don't get termination of proof search. On the other hand, if you have a look at the cut rule, then if you go from the conclusion to the premises, you have to somehow come up with the cut formula A. And there are infinitely many formulae, so you have infinite branching in the search tree, basically. So these two rules are not good for proof search. Okay, also the cut rule makes a mess out of the subformula properties, so we somehow want to get rid of them. So this leads us to considering a sequence system good in our sense here. If in this sequence system the cut rule and the contraction rule are admissible, meaning that if we drop those two rules, we can derive the same set of sequence as we can with those two rules. Okay, now it's not always possible to, or not all sequence systems have this property that the cut and the contraction rule are admissible. So what we would like to do is we would like to somehow come up with some general criteria which ensure that this is the case. So which ensure that we can drop the cut and the contraction rule. And the idea here is to have a look at Gensen's original proof and somehow extract criteria from this. Okay, the main notion in this construction or in this criteria is the notion of cuts between rules and contractions of rules. So this is more or less a lifting of the cut rule as a rule on sequence to an operation on derivation rules. So now we can take two sequent rules or derivation rules and apply an operation to them, and we get a new rule. So I'm not going to give the details, but the intuition is this. Well, it can be captured in the slogan, first cut the conclusion and then cut the premises. So the idea is if we have two rules, like the for rule on the left-hand side and the k rule on the right-hand side, so you see we have a formula box A, which occurs on the right-hand side of the for rule, of the conclusion of the for rule, and on the left-hand side of the conclusion of the k rule. So we could apply the cut rule to these two sequences. And this is exactly what we do. So we cut the conclusion, we arrive at the sequence at the bottom here. And, well, now you see that there is the formula A occurring on the right-hand side of the premise of the for rule and on the left-hand side of the premise of the k rule. So again, we can apply the cut rule. We do this, I wrote this here like in an upwards way, and we take the rule which we get if we take the red premise and the red conclusion to be our new rule. So this is a quite basic concept of cuts between rules. Okay, maybe I should mention that this part be liberal in the slogan here refers to the context restrictions. So what we want to do is we want to be as liberal as possible in the construction of the premise. So this is seen here that we carry over the context restriction box gamma from the premise of the for rule. So we take the most generous restriction, basically.
Because these things are right here, right? But these could be pretty far away. I mean, to be liberal, to cut rules.
You mean in a
Search, yeah. You may need to find the B.
Okay, so this is not a part of the proof. This is an operation on sequent rules.
Normalization procedure.
Not really. So it's a means of taking a set of sequent rules and then adding a new rule to it. And then with a new set of sequent rules, you can have proofs, derivations.
Oh, it's not a normalization.
No.
Saturate, do you continue this procedure?
Yeah, that is basically the idea then.
Saturate this.
Yeah. That's going to be in the next slide. Okay, so we can do the same thing or analogous thing for contraction. So we have a formula where we can contract the conclusions and the premises. Now we do this, we end up with a derivation rule, which is shown in red. Well, this is basically the same thing for contraction. Okay, now we're in a state to formulate the criteria for cut elimination. And the first criteria is exactly this saturation criteria. So this, let's say that a set of rules is principal cut closed if it is more or less closed under this operation of adding cuts. So the meaning that the cuts between two rules, well, they don't necessarily have to be in the rule set, but they should be derivable in the rule set using contraction and cut. Then we have some other criteria. So intuitively, context cut closed means that whenever we have a situation that we have two sequent rules and we can cut, or like two applications of sequent rules, and we can cut in the conclusions onto context formula, then we can either push the cut up into the premises of the first rule or into the premises of the second rule. Let's furthermore say that a set of rules is mixed cut closed if, well, we have a cut between two conclusions of sequent rules. The cut formula is contextual in the first rule and principal in the second rule. Then we can push up the cut into the premises of the first rule. All right, contraction closure means saturated under this operation of contraction on derivation rules, and saturated means we have all these properties. So if you know the standard Gensen cut elimination proof, then you will see that this is exactly what you need in order to make the double induction go through. And well, this is exactly what you get. If you have a saturated rule set, then you get cut elimination. And furthermore, once we have done this, we can apply some standard trick and copy the principal formula from the principal formula into the premises. And then we get admissibility of contraction as well. So we can get rid of the contraction rule. And furthermore, if the rule set is tractable in some very mild sense, then we get decidability as well. And we don't only just get decidability, but we get a generic complexity result, namely that for saturated and tractable sets of rules, deciding the derivability problem can be done in exponential time. Okay, so this is good. Now we know what we consider to be good sequence systems. Now, of course, the question is, how do we construct good sequence systems? And so one of the main things is this nice lemma, which simply states that this operation of adding cuts between rules to the rule set preserves soundness of the rule set. So, well, provided we have propositional logic, we can just take any two rules of the cut set of the rule set, apply cut, add the new rule to the rule set, and we don't lose soundness. So this is good. This suggests basically saturating the rule set under cuts. So we take a set of rules, we add all the missing cuts and contractions. This guarantees principal cut closure and contraction closure. And then what we are left to do with is checking for context cut closure and mixed cut closure and tractability. Where tractability usually is not that much of a problem, because if you saturate the rule set by hand, then you will have some kind of pattern, and that usually is tractable in our sense. Okay, now of course, I should mention that we have applied these heuristics to, well, I guess this heuristics has been applied many times, but we have applied it to conditional logics, namely VA, Lewis's conditional logic VA, and a number of logics extensions up to VA. Lewis's conditional logic V and a number of extensions up to VA. And we got cut-free sequence systems for these, and these can be used to show interpolation, for example, as well. Well, now, of course, the question is, how do we get a set of sequent rules to start with? I mean, this procedure only works once you have a set of sequent rules which you can then saturate. But how do we get the sequent rules? I mean, usually the modal logics are given as a set of axioms in a Hilbert-style system, right? So a number of formulae, and you close these formulae under modus ponens and under uniform substitution, and then you get a logic. And now how do we get the sequence-style system out of this? And the idea here is basically similar to the one which we had for the cut elimination theorem. We want to find some general criteria which allow us to state that a formula is translatable into a sequent rule. Okay, let's go through two examples. I'm not going to give you the criteria. They're in the proceedings. But let's have a look at an example to see how the translation works. So we are going to consider this maybe very basic example of constructive modal logic S4. So this is intuitionistic propositional logic together with the two axioms, box P implies P and box P implies box P. And we're only going to look at the box fragment of this for the purpose of this talk, so you can have the diamond as well. This is in the proceedings as well. Okay, so let's assume we have the standard rules for constructive modal logic K. So this is, basically the standard rules you would have. Suppose we have already constructed them. Then let's start converting the axioms into sequent rules. And let's start with the T axiom, because it's a little bit simpler. The idea is that this does not involve nested modalities. And this makes it much nicer. So what do? We take the axiom box P implies P. And the first step is we turn this into a zero premise rule in the sequence system by writing it on the right-hand side of the turnstile and basically allowing no premises. And now this is not yet a rule in our rule format because it involves propositional logic in the conclusion. And we only had modalized variables in the conclusion or in the principal formula, right? So, this can be dealt with. What we do is we break up the propositional part, we break up the implication. At this point, one has to be a little bit careful because we're working on intuitionistic logic and we cannot always do this. So this is the reason why we have some criteria. In classical logic, we can always do this, right? So we can always invert the propositional connectives. But with intuitionistic logic, this is not quite as simple. Nevertheless, if the formula satisfies certain criteria, then we can do this. We end up with a sequent box P entails P. And again, this is not yet a rule in our sense because we have a propositional variable in the principal formula, and we are only allowed to have modalized variables. So this can be dealt with as well. We have the idea is to take the variable, which in this case sits on the right-hand side of the turnstile, and to introduce a new premise with this variable on the left-hand side on the turnstile, which copies over the whole context from the conclusion. So if we do this, then one can show or see that the two rules are equivalent, so that they derive the same sequence, and we get a sequent rule in our sense. So the restriction is the restriction with singleton P in both components. And this strategy actually yields criteria for when non-nested axioms over intuitionistic logic are translatable into sequent rules in our sense. And the criteria mainly have to do with resolvability of propositional logic in this step. Or we could also have a propositional formula here, and then we would need to resolve this. And Okay. A small remark. What we get is is a simpler form of the rules with context restrictions, because in this case we only get rules where the context restriction either copies the whole context or copies nothing, so no part of the context. And so this is nice. We get this is what we call shallow rules, because they basically don't allow for nesting. And actually what we're thinking about at the moment is how to translate shallow rules, or in general rules with restrictions, back into axioms. And for shallow rules, we can actually show that or at least I think we can show that the criteria which we give in the paper are necessary and sufficient for translatability. Okay, a second remark, if you work on Okay, thanks. Second remark, if you work over classical propositional logic, then you can always break up the propositional connectives. So you get the result that every non-nested axiom can be translated into a sequent rule. Okay, but let's have a look at a little bit more interesting example, namely the for axiom. And so we have the axiom box P implies box P. And here the key observation is that we have a formula, in this case box P, which occurs both on the top level of the axiom and under exactly one modality. So in this sense, the axiom is, well, basically non-nested. It's just a substitution instance of a non-nested axiom. So we can use some of the techniques which we had for non-nested axioms to translate this axiom into a rule. Okay, let's see how this is done. Again, first we take the axiom and we resolve propositional logic, and we take we write it as a zero premise sequent rule. So we get the rule with box P on the left-hand side and box P on the right-hand side of the sequent. And now what we do is this: we take the occurrence of the formula, in this case box P, which sits under the box, under the modality, and we introduce a fresh variable for it. So we substitute it with a fresh variable Q in the conclusion. And well, now we have to add some premises which state that Q is equivalent to box P, but we can do this. And okay, in the next step, we can make use of the fact that in this case we have a monotone modality, right? So we can make use of this fact and eliminate one of the premises. So this is a general thing. In this example, it's the right-hand premise. And well, in this case, we're lucky because the formula box P ends up on the left-hand side of the premise and on the left-hand side of the conclusion. So this already looks suspiciously like the for rule, right, where we had a boxed context on the left-hand side of the sequence. But again, this is not yet a rule in our sense, because we have a formula box P on the left-hand side of the premise, and we are allowed only propositional variables. But we can turn it into a sequent rule by making use of the concept of cuts between rules. So we take the standard K rule, which is this one, and now we can compute the cut of our pseudo rule with this K rule on the formula box Q1, and we end up with the rule on the right-hand side, or the pseudo rule on the right-hand side. And well, you can see we can do this iteratively, and we can one by one replace all the Q2 or the QIs in the premise by box PIs. And since we can do this for every number n, in effect we get the context restriction which copies all the boxed formulae from the left-hand side of the conclusion into the premise. And this is exactly the for rule which you have in standard modal logics. Okay, again we get a strategy for the translation. Here it's not quite as nice to produce some criteria, but yeah, this is at least a tool for translating axioms into rules. Okay, in the proceedings you will have some other examples, some access control logic or some conditional logics, but I'm not going to tell you any of these now. All right, so let's sum up. What do we have? We have a generic rule format which seems to encompass most of the standard modal logics. We have some general sufficient conditions which guarantee cut elimination and decidability. And we have some general criteria and tools for translating axioms into sequent rules. And then, well, maybe the nice thing is that all these results work for modal logics based on intuitionistic logic and on classical logic. Thank you for listening.
Is contraction closure in all this? I mean, I see the thing for cut elimination. Supposing I'm working in a logic where I can't get rid of contractions.
Okay, so
would I still be able to bound proof search somehow?
Okay, so
using this kind of methodology, I'm saying.
Yeah, so for example, for proof search, actually, so we need contraction closure because otherwise we wouldn't be, I mean, you could keep on searching forever, right? Because the branches could be infinite in the proof.
Termination
Yes, you could. You could. I mean, it's probably... So these are sufficient criteria and not necessary criteria. So you could very well have a sequence system which does not have, or where you don't have admissibility of contraction, but can prove termination of proof system, of proof search by any means.
Do you think your method can be extended to systems, a more general system other than this classical and intuition framework?
Yes, it can, and okay, maybe I didn't make it clear enough. So the rule format is very generous, and it just, well, the classical rules for standard modal logics are instances of that rule format. But we also have conditional logics, for example, Lewis's logic V, and VT, Vn, VW, Vc, and also Va, where the rules fall under this format of rules with restrictions, and we can use all these techniques to get a cut-free sequence system for these logics, and we get termination of proof search, we get an optimal p-space complexity bound in the case of all the logics except for Va, and we get an exponential time complexity bound for Va.
And this is holds for linear logics and substructural logics too?
Okay, I haven't looked into substructural logics that much. The problem is that for many of the things we need some propositional logics, some underlying propositional rules. Plus, in some instances, we actually use contraction in the proofs. So if, for example, you drop contraction, then I'm not sure whether everything works. But I haven't looked into that thoroughly enough. But theoretically, I would imagine that these methods could be extended to cover substructural logics as well.
So when you do the saturation, how much is the size increase? The set of rules?
The size of the set of rules? Very much in general. So because in general you get an infinite set of rules by saturating. So if you start with the K rule, okay, so with the, okay, if you start with the K rule here, you see it has n instances of box Q on the left-hand side of the turnstile. And if you cut this with itself, basically, what happens is you add more instances of more Qs to the left-hand side of the turnstile, right? So your size increases. You still have somehow the same schema or the same pattern of rules, but you get infinitely many rules. So yeah, if you start with the axioms for modal logic K, you get an infinite rule set. But that is not that much of a problem because you have some pattern, and this pattern is tractable in our sense. So we can actually use this rule set, and you could even implement it and for backwards proof search.
So I had a question. So you had a Dex time complexity result. Can you also extract conditions to get lower complexity? If your original rule set has some other properties, can you get p time, for instance?
Okay, I wouldn't think so. Okay, one thing is if you have context restrictions which are very simple in the sense of a shallow rule. So this was the last slide, I think. Yeah, if you have a shallow rule or set of shallow rules, meaning that the context restrictions copy either the whole context or nothing of the context at all, then we actually get a p-space complexity result for proof search. And in general, we won't be able to do better than that because the standard modal logics are complete for p-space, right? So it's not clear. In the more general case with restrictions, we're actually not sure whether we can lower down the exponential time bound to p-space. I mean, again, we won't be able to get below p-space, but it might be possible to get it to p-space. I'm not sure.
Let's thank the speaker again. So the next talk is by Franco Parlamento, and the title is Cut Elimination for Gensen's Sequent Calculus with Equality and Logic of Partial Terms.
While we are waiting that this machinery starts, I'd like to say that this is my first visit to this incredible country. The first was about 20 years ago. And I'd like to say that I think this conference is so nice and well organized, is a highly visible sign of the progress that has been done since that time to promote the study of logic in this country. So thanks to the organizer. This is one more reason to be pleased to be here with you today for me. Oh, the content of this talk would be most technical, since it will be devoted to the proof of a single theorem, Cut Elimination theorem for Huygens and sequent calculus for equality. But it is a sort of side result that we obtained while trying to carry through a proof-theoretic analysis of the logic of partially defined terms. So perhaps I will say first something about this project that we are carrying through, and then get into the details of the proof of cut elimination. When I speak of partially defined terms, I'm thinking of a situation like this difference in the natural numbers, or the cardinality operator, or operations in the set theoretic universe in ZF, which are naturally undefined in various cases. Classically, you can reduce this situation to the case in which they are totally defined, but that is not particularly natural, and it requires the law of excluded middle, and so it's natural to try to reflect directly the way we can reason about these things, leaving them undefined. For another case, look at this choice function operator, which applied to a set X, it gives you a choice function on X, if there is one. And otherwise, it remains undefined. So the goal is to show that the addition of these operations to the theory PA or ZF yield conservative extensions. Yields conservative extension. But of course, you have to set the logical ground appropriately for this to happen. But the solution is quite simple if you look at things proof theoretically. It suffices to restrict the for all elimination and there exist introduction rules to variables rather than arbitrary terms. And of course, you have to decide what to do with equality, and the simple solution is to add reflexivity and this, which I call congruence rule, which are the obvious counterpart of the standard axioms for equality in Hilbert-style systems. This is essentially what you have to do. In the issuistic case, though, you need something more to have conservativity for this particular case. For those cases, you don't need anything else, but in this case, you need also this axiom, this sort of determinacy of equality. and then you're done. So our project is carry through the proof theoretic analysis of this system and show that actually you get intuition conservativeness. So you can freely use these partially defined terms and be sure that you are on a logical ground, so to speak. I'd like to remark that reflexivity is assumed for any term, even if they are undefined, like it could be 1 minus 1 before 0 was born, or 1 minus 2 before the negative integer were born, or this kind of congruence relation. When thinking of or about partially defined terms and taking the existence as a primitive predicate, one often looks at a strict equality in which you require that the term has to be defined for t to be equal to t. This is not the position here. Or also it is looked at a lax equality in which you say that if one term is defined and the other is defined and they are equal, and conversely, but that would force 1 minus 2 to be equal to 1 minus 3. This seems to be too lax in this perspective of capturing the development of mathematical discourse. So this idea that this could be a good framework, it's not particularly new. I think it goes back at least the end of the 50s by LeBlanc, Halperin, and Hentica, and possibly others. But I don't think it was much developed, neither from the semantical point of view nor from the proof theoretical point of view. From the semantic point of view, if you are interested in a proof of conservativeness, you can look at this, this work of mine, which gives a semantic proof in the classical case, but I think it could be extended to the intuitionistic case too. But now let's go back to the main topic of the talk. And I call L equal and LC equal the sequent calculus which have structural rules and logical rules as in Gensen's Lj and Lk Untersuchungen. In particular, I take Gensen has these rules, not with terms here in his investigations. Actually, he has parameters rather than variables that makes a distinction between bound and free objects. For the reflexivity axiom, we have this, and the congruence rule would be this. Well, this is the natural counterpart in sequent terms, but this is the natural deduction rule that I showed you before. And this system, of course, is not particularly good for proof search because you see it makes the equality disappear. And, oh, sorry, I meant to show more slowly the rule. It eliminates equality, so it is not in the sequent calculus spirit, this, so to speak, this rule. What it is in the sequent calculus line of thought, it is, well, you can consider this as the rule, zero premise rule, which introduces equal on the right, and you can take this rule, which introduces equality on the left. This is easily seen to be equivalent but using cuts with the previous system. But it is not enough. If you have these two rules, then you don't have an adequate system because you won't be able to prove the left symmetry rule. This is an easy-to-check counterexample to this. So we have to use something. This is the choice we propose. So our system is now settled. It's sequent calculus with this further axiom and these two rules. This for left introduction and this symmetry on the left. What about total logic? Well, if you want total logic, you simply add axioms. They make every term defined like this. And this is equivalent to adopting these rules. The usual for all. Oh, there is a mistake here. Of course, this is, you have to revert this. No, okay, I'm sorry. Yes. What do I want? No, it's okay. It's okay. Okay, sorry. This is equivalent, and so in this way you see total logic as logic plus every term exists in agreement with Quine's dictum, no? to be the value of a variable. The system I showed is somehow related to the system introduced by Stig Kanger back in '63, and for which, or proof of cut elimination was the project of Lifshitz, which, though it never appeared, what Lifshitz showed, it was the system they consider is something like this, where you have many substitutions. You could see that having these two, R2 can derive from R1 by using the left reflexivity rule. You could also see that the reflexivity rule is admissible here. So the Lifshitz work was the one who actually appeared at this goal, wanted to show that monotonicity theorem, trying to prove the cut elimination theorem, but the second part apparently never appeared. So our approach is going to be different. It goes like this. These are things that you can get from Lifshitz's work, essentially. You can reduce the cut to act on atomic, the congruence rules to act on an atomic formula only. This requires cuts to begin with. The logical axioms, as usual, can be taken in atomic form. And furthermore, you can have only atomic logical axiom and cuts, and no logical inference above cut or congruence rules. So you put cuts and congruences all above the proof. And this, it yields a reduction to a purely equational systems like this. And the first thing that we could remark it is that here you don't have any difference really between classical and intuitionistic logic in this purely equational subcalculi. And here is where you want to prove cut elimination. A further reduction is that the congruence can be restricted to the case in which you just replace one occurrence of a single variable. This is all useful technically. Here are a few other rules that you can consider and are useful for the proof. left symmetry I told you about. You have right symmetry and the left congruence rule. They are the obvious things. Here are some results that are needed. Those in boldface and blue are those which we actually need. And just to give you the idea of how these proofs go, I spent a minute showing this last. The left congruence rule is admissible in the monic equational calculus. It goes like this. Well, the contraction rule is there, so you have to take care of multiple occurrences of the formula you are interested in. I use this notation, gamma sharp A, for a sequence like that, where gamma is just what you can read there. And you prove this, that if gamma sharp f of r sequence D is derivable, then this is also derivable. You go by induction on the ith of derivations, and for example, if it is an axiom, then you use this other axiom and use the congruence rule, and you deal with this problem. When you go to the induction step, the less trivial case is this one. This f of r is introduced. It has this form by a congruence. This is what you want to prove. Then you start with that you have by induction. And you proceed in the following way. So this is one result. Maybe this is a second one. Maybe I skip this proof. It goes by induction in this system. And here what you prove is this, namely, well, it's better to work with a non-sharing version of the calculus in doing this proof. But here you have the structural rule, so it doesn't matter, you can do it. And you have to prove that if this and that, the premises of the two premises congruence rule are both derivable, then the conclusion is derivable in the cut-free part of the theorem. This it goes again by induction. The base case, it is not so trivial, because there are two ways in which this reflection axiom can be seen as the result of substituting R for V in the formula F. It could be R equal V or V equal R. In this case, F of S is either this or that. In the first case, it's obvious, and in the other, it follows from an application of the symmetry rule, which is admissible. It has been proved before. This is the less trivial case. Basic case, but less trivial, because the axiom is like this, and then you have to apply the previous lemma if you think of it for a moment, the one I went through rapidly through the proof. When you go to the induction step, here I'd like to show in some more detail what to do. This is the case in which it is the less trivial case. The gamma is gamma minus p equal q. It is there because of a congruence, monic congruence rule. In this case, this G of uq, it can be seen also as f of VR. And then you have to distinguish three cases. The first one is the one in which R and Q do not overlap. You can see G of UQ as f of VR, but Q and R do not overlap. Then the situation is this has this form, G of UP is this other form, G of UQ as this other form. And then, by induction hypothesis, what do you have? Remember, we have a proof of lambda sequent R equal S as the second derivation of lambda R equal S. We apply that to the premise here, and we get this conclusion. And from there, we can easily go to the conclusion we want. This is the simplest of these three cases. I'd like to show you by picture this. Here it is what we have as the premise. The term looks like this. If you use this equality over there between those terms, then we obtain this. So this is how the derivation ends. You have this congruence rule, which leads to this picture, to that picture. Also, we have this derivation, which is under lambda establishes the equality of these two terms. And then, if we apply to this, this equality, this is what we apply the induction hypothesis to this and this. The result is this one. And finally, to this one, you apply the congruence rule, and you obtain what we wanted. This is f of s. Okay, and this is the sequent. So this is the easiest case. I skipped the second one. Well, case 2 would be the case in which R is part of Q. Case 3, Q is a proper part of R. Now, let's go just by picture here. What you have, it is a derivation which ends with a congruence. This was the first premise. This one, well, you introduce on the left the equality P equal Q. And so you obtain this. But you see now the term R, which you are going to replace, gets into the picture in this different way with respect to the previous case. Still we have here the equality lambda sequent R equal S. R contains Q. And so the picture is this. And then, if we proceed differently from the previous case. We have to apply congruence between that and this, and then to obtain this other sequent, which is the equality between these two things. Okay? And we obtain this equality. So we work inside this term. And from this, we again reach the conclusion. Okay, so it's just a matter of playing with these terms. You see, it's very useful to have only one occurrence of a variable. in doing this replacement. And so this, okay. It's almost the end of it because we have admissibility of the natural deduction format of the calculus for equality into the, so to speak, real sequent calculus version of it. And due to the lack of introduction rule on the left, different from weakening, so the cut rule is easily seen to be admissible in EQ deprived of such rules. I'm taking a different route from the one on the proceedings here. There, I obtained cut elimination for, we obtained cut elimination for the monic system and then went back to the natural deduction system. But it is much more effective to go this other way around because this is really easy. Not having this introduction rule on the left, it makes it even contraction and cuts very easily eliminable. But one, says then equality is eliminated. The system is not good for proof search. But if you look at it this way, cut elimination is easy. The main point is to get admissibility of that rule in the monic system. Let's, so to speak, the serious one. And then you get cut elimination for the monic system in the following way. You take a derivation in this system, then you can translate it into a derivation in EQ plus sim L, the monic system, because the rule here is derivable even without cut from the natural deduction rule. Okay. But here you have sim L. But sim L is admissible in a EQ. So you go to EQ, then you eliminate cuts, and which is easy. And then by admissibility, you go back to the cut elimination for this system. Then the Stick-Kanger, we have cut elimination for that system too, and you can make, of course, applications very simple like this one. For example, if you want to have conservativity of logic with equality over logic without equality, in this system, it's the monic system, this is an obvious result because no rule eliminates equality. So if you don't have equality at the end, in a cut-free proof, you don't have equality anywhere. There are another couple of remarks that one can make just by looking at cut-free proofs of this sort. So here the cut elimination goes like this. For the full systems, where you have the logic, I explained you how to push equality and congruence all up above, no cuts below, and you eliminate cuts there. So I think that's one final remark concerning such cut-free proofs. And so I think just thank you for listening.
You have time for one quick question?
The question is a bit, not exactly on this issue, but it is on equality. So perhaps you would answer. The question is the following. There is some problem with equality and identity. You know that identity, because equality doesn't really represent identity. Now, when you talk about cut eliminability or equality in the context of sequent calculus, then does it really help in the solution of the problem of equality and identity? I'm not sure whether I could convey my point.
Probably not. No, I don't think it does.
Let me repeat. In the say first order logic, we have equality axioms, but the equality is not exactly what we understand by identity. Because you have that model.
But yes and no, because if you take this second order principle of indiscernibility, then you probably...
That is the, okay, so you have to take another principle
So
then.
this is kind of a projection of the first order floor of something more general.
Yeah, but still then
So
you
I
see...
don't think cut elimination by itself it doesn't solve the problem you have. Provided I
Perhaps
understood what it is
you
the
have to
problem.
discuss
should,
this.
Okay.
Okay.
Yeah, we are running a bit late, so we'll move on to the next talk. Let's thank the speaker again.
Thank you.